Good to see these. So I hope the projects are proving to be useful to you. It's really a key part of this course because we want by the time you come out of the course that you understand the key algorithms and underlying theory, but also that you have some experience with trying it because, as you know, when you work with real data, things are always a little bit more grounded than when we talk about these algorithms in the abstract. So I hope that's useful. Anyway, I look forward to reading these. That's going to be good. So today we're going to finish up our treatment of support vector machines and also tie them back to a number of topics that we've discussed along the way in the course, like comparing them to some other algorithms, relating them to pack learning theory, and so forth. So let's get started. So last time we got to the point where we had defined support vector machines as a way of doing classification. So it's a discriminative classifier, just as, say, logistic regression is a discriminative classifier. We're trying to learn some function from x to y. And in the case of support vector machines, we define the objective function that we're trying to optimize in order to choose the weights for that function as the function that ends up with the largest margin, gamma. The margin being the distance between the decision surface and the closest data points. And we had just, at the end of last class, got to the point where we realized that we could express that margin in terms of the magnitude of the weight vector, W, and the value of the function at the nearest point. And we proved that. We derived it, actually, at the end of last class. So this is useful to be able to express the margin in terms of A and W because when we try to maximize that margin, essentially what that means is we want to minimize A over the magnitude of W. And then one further step, it turns out that, well, to be more precise, what we want to do is we want to classify all the examples correctly and maximize the margin. So we could say that our objective is actually this. We want to choose the weight vector W and also the constant B such that we maximize that margin. We want to choose the one that maximizes gamma, but such that we classify all of our training points correctly too. And recall that in the case of support vector machines, instead of saying that y is 0 or 1, we say y is minus 1 or 1. So the negative examples, we're going to give them a value of minus 1 and the positives a value of 1. And so a nice little way of saying that we want to classify each of our points correctly is to say that for training point xj, we want to make sure that the weight vector times xj plus b times y, well, y is either going to be plus or minus 1. So if it's a positive example, it'll be plus 1. And so we want that wx plus b to be greater than a. That'll put it on the right, the correct side of our decision surface. On the other hand, if y is minus 1, then we just want that essentially the negative of this to be greater than a. Okay, so that'll put it on the correct side over here. So this multiplying by plus or minus 1 is just a way that allows us to have a compact way of expressing the kind of intuitive, the obvious intuitive constraint that we want all the positive examples on this side of y plus x, wx plus b equals a. We want them on this side of it. And we want all the negative examples on this side wx plus b equals minus a. Okay, so there's our objective that we want to maximize. And this note here simplifies life for us further. If we have this kind of a setting, what I could do is I could just divide through by a. So basically, I can say that my margin is going to be 1 over the magnitude of w, and I'll make this greater than 1. So in other words, I can just arbitrarily say a equals 1, and I can make it so just by scaling w's appropriately when I choose them. And so it makes a slightly more simple function to consider if we just divide through by 1, and we essentially just assume a equals 1. We just assert that. And so then that gives us, just rewritten with a equals 1, that gives us this. And that lets us see that actually the margin, if we define a to be 1, then the margin is just 1 over the magnitude of the weight vector. So the bigger the coefficients in W are, the smaller that margin, given that we've labeled our examples correctly. And if we want the largest margin, we want the smallest W. Again, given that we're labeling the examples correctly. And it kind of makes sense. If you think about the distance we'd have to travel from wx plus b equals 0 to get to it being 1. If I'm considering the weight vector pointing in this direction, or this, or this, or this, or this, the smallest weight vector will make me have to travel the furthest distance to get from 0 up to 1. So in that sense, it makes complete sense that the smaller the magnitude of the w vector, the wider the margin, the further I'll have to travel from the point where the function equals 0 in order to make it be 1. Okay, so there's our objective function. And typically, we write it actually this way, where we just take advantage of the fact that if we want to maximize 1 over the magnitude of w, that's equivalent to just minimizing the square of w. So w transpose w, again, if w is just a column vector, then w transpose w will just give us the sum of the squares of the weights in w. So essentially, it's just saying minimize the sum of the square of our weights such that we correctly classify all the training examples. Okay, so it's just a mathematical way of saying label everything correctly and find the largest margin you can among the different linear surfaces that will label things correctly. All right, so now the nice thing about writing it in this form is it turns out this is what's called a quadratic programming problem. So there are optimization algorithms around that you can grab off the shelf. This is a well-studied class of optimization problems where essentially this is called a quadratic programming optimization problem because the quantity that we're trying to minimize with respect to our variable, in this case w and b, is a quadratic function of w and b. Quadratic, yeah, we just said it's the sum of the squares of w's. Quadratic function of w. And a quadratic programming problem is one where we're trying to minimize some quadratic function of the variables that we're selecting over, such that we satisfy a number of linear constraints. When I say linear constraint, I mean, I mean linear in W. Okay? So the linear constraints are linear in the variables, again, that we're trying to optimize over. So that's a great class of optimization problems because we don't have to write the optimization algorithm. People who are very smart have worked on these kind of optimization problems for a long time, and they can be solved. And furthermore, they have a local optimum, which is also the global optimum. So if we can optimize it, we don't have to worry about local minima. So this is a great objective function for us on both scores. There are good algorithms for solving it, and if we can find a local optimum, we get the global one. Okay? Okay, so that's the primal form. And if we can just solve this, we're done. And if we do that, then we will be doing what I would call the non-kernelized version of support vector machines, right? We're working in some space X. We're learning some weight vector W. And we're learning a linear classifier of the points in X. Now, you recall our discussion of kernel functions. We said, well, kernel functions can be useful to us if we actually want to operate in some higher dimensional space and find linear classifiers up there in some space where we project our X up into some higher dimensional space. And then the great thing about kernel functions is they give us a way to do that efficiently by staying in our ground space and working in this kind of virtual way in the expanded space. But to do that, we had to, when we did linear kernel regression, the first thing we had to do is we had to go from the primal form of our optimization problem to make up this dual version of the optimization problem, where the dual re-expressed this in a way that we only had to compute dot products of the x's. So we can do the same thing for support vector machines. In fact, if you think about it, support vector machines are just like linear regression. That's really what we're learning. We're learning a w times x plus b equals some constant. We're actually learning a linear regression function, but then we're just classifying our examples by saying, once I have the learned function, if I have a new test point x, I just apply wx plus b to that test x. If it gives me a y that's positive, I'm going to call this a positive example. If it gives me a y value that's below 0, I'm going to call it a negative example. So I'm just basically thresholding the y value, which is some continuous output variable that I get when I do wx plus b. So it's linear regression in a way, but then I'm just thresholding it to do the classification. So all of the stuff that we talked about for kernel linear regression applies here almost exactly the same. It's a little different because the objective function that we're trying to solve here is not actually the same as the objective function that we set up for our linear regression. Instead, we have this maximize the margin objective function. So we need to find the dual of that. And here is the dual of it. And the reading for this lecture and the previous lecture, which is Chris Bishop's chapter on support vector machines, does a nice job of deriving this. We're not going to go through that derivation in class, but it is a worthwhile thing to take a look at that if you are curious about how you would actually derive this from that. But let's look at the form of it because it is kind of interesting. So basically what we're saying is this dual form of the problem gives us the same linear classifier if we optimize the dual form as if we optimize the primal form. And instead of saying we're going to minimize the square of the magnitude of w subject to those labeling constraints, now we say, well, first of all, we're going to classify our examples not with wx plus b, but just as we did in linear regression, we're going to sum over the training examples, the ELF training example. Actually, I call these support vector here SVs for support vectors. We'll come back to that. I could equally well have written this sum over all the training examples, L. And what am I going to sum? So I want to classify some new test example X. What I'm going to do is I'm going to take the dot product of my new test example X with training example L, multiply that by plus or minus 1, depending on the label of training example L, and then some coefficient alpha, which is going to be positive. So basically, I'm multiplying it times, I'm dot producting X with training example L, and then giving it some weight alpha and some sign plus or minus, depending on what whether this was a positive or negative training example. Plus B, my constant. And then, of course, if that quantity is above 0, I'm going to label my new test X positive, otherwise negative. And if you recall, this is very similar to the form that we used when we did kernel linear regression, or the dual form of linear regression. And so that's how we're going to use what we learned from the optimization. And the optimization problem itself is this. And again, well, it's not the same as the kernel linear regression dual form. But let's take a look at what it is. These alphas, of course, are going to end up being the weights. We're going to learn a different alpha for every training example. And they're going to end up being the weights. And what we're trying to do is we're trying to pick the alphas for the m different training examples that maximize this expression. So the first thing is just the sum of all those alpha values. But then we're subtracting out this thing, which is, so again, J and K here are just indices over the different training examples. So basically what this objective is that we're trying to maximize is the dot product of every pair of training examples. Xj and Xk are two training examples. I'm summing over all J's and K's. So for every pair of training examples, I have a term here that's being multiplied by Yj times Yk. So what does that mean? If they're the same label, Yj equals Yk equals plus 1, say, if they're the same label, then Yj times Yk will be positive 1. If they're different labels, then it'll be negative 1. And then they're alphas. The product of their alphas. So I'm not sure there's a simple intuitive way to justify why this is the dual form. Again, you can look at Chris Bishop's chapter to see the derivation. But you see what's involved computationally is essentially looking at dot products of all of the different training example pairs, taking into account their labels, and then choosing alphas that maximize that expression subject to these constraints. We want all the alphas to be non-negative. It's okay for them to be 0. And we want the sum of the alphas times the labels to be 0. So what does that mean? One way to think of that is if we take all the alphas for the positive examples where y equals plus 1, we want the sum of all those positive example alphas to be equal to the sum of all the negative example alphas. If that happens, then this sum is going to be 0. Okay, so it's sort of like we want equal mass put on the positive side and the negative side of that decision boundary. And that's it. That's the dual form. And by the way, to get this b, which you don't see here in our objective function, involves a second step. Once you solve for the alphas, then by essentially taking advantage of the correspondence between the primal and dual, you can calculate what the B's are. And again, Bishop's book goes through the detail of how you would derive those B's given the alphas. But it's important to notice there is no B up here in our objective function. So getting that comes as the second step once we have the alphas. Okay, so why is this good for us? Well, for the same reason that the dual form was good for us when we did kernel linear regression, which is both our training and our use of the function that we're learning depends only on taking dot products of training examples. There's no other kind of operation that we really need to do. And so once we've got it in that form, we can bring in the kernel function and replace those dot products by kernel products. So talk about that in a second, but first let's come back to that point about support vectors. So when I wrote the expression for how we're going to label our examples, in the primal form, we'll test if the Wx plus B is negative, or equivalently in the dual form, I said we would look at these dot products of the new test X with our training examples X sub L. But then I kind of slid right over the fact that instead of saying the sum over L in all the training examples, I just said the sum over L in the support vectors. What do I mean? What I mean is this. The support vectors in this data set are these three that have circles around them. And those turn out to be the only training examples we need to sum over in order to classify the new test example, whatever it is. And the reason is all these other data points here have alphas equal to 0. They will have alphas equal to 0 when we solve the dual form of the optimization problem. So this is kind of an attractive property of support vector machines. It means that if I have 10,000 data points here, when I go to classify a new example, I don't really need to take the weighted sum of alpha times the dot product of each of those 10,000 training examples with my new example. Instead, if it's a plane, all I'm going to need is to take the dot product of, I'm going to find that all the alphas are 0 for all of those training examples except for 3 of them. And all I will really need to do to test my new example is take the dot product of the new example with each of those 3, multiply them by their non-zero alphas, and use those. So this is kind of a neat property. And one way to think about it is just this. Obviously, if what we're trying to do is think in terms of the primal problem. What we're trying to do is find a decision surface with maximum margin that correctly classifies all the data points. Then it really wouldn't matter if I moved, say, this data point up here instead. That won't change the margin. It won't change the decision surface. Obviously, the decision surface doesn't depend on that point. In fact, it only really depends on these 3 points that kind of hem in the decision surface. Okay, and therefore, that's one way to think of it. Another way to think of it is, that's a good way to think of it. You can also, if you have some pencil and paper, realize how you can express Wx plus B from just the coordinates and values of these 3 points uniquely. So, but basically you see that it's pretty intuitive. That decision surface doesn't really depend on anything except those 3 points. Does that make sense? Good. Okay. All right. Now, I just mentioned that if I had 10,000 points in this two-dimensional plane, I'd only need 3 support vectors. And nobody gave me any pushback on that. So I assume that's because it's pretty clear that 3 will do it. Right? If I tell you what the 3 support vectors are and their labels, then given no other information about the training state, you can always figure out what the decision surface is. Right? So what if it's a d-dimensional space instead of a 2-dimensional space? D plus 1? I hear votes for D plus 1. D plus 1. So if it's like a 3-dimensional space, that means we have to specify a plane. I'm claiming 4 points will do it. For example, those 4 points. If these are the support vectors, there's only one plane you can get that will be the same distance from all 4 of these points. So the support vectors are the points that lie right at the gamma value. Well, actually, in our case, gamma away from the decision surface, or they have the value 1, given that we defined our objective function so that this equals wx plus b equals 1. Yes?
So does it mean the SVM is very sensitive to noise? I mean, if the data change a little bit, if the negative one goes into the positive one's group, it may not find a boundary.
Yeah, that's a great question. So the question was, doesn't this mean that our decision surface is going to be very sensitive to little changes in 1 or 2 training examples, and maybe therefore very sensitive to noise? It is sensitive to those, especially if we only have a handful of training examples, but then every learning algorithm will be. On the other hand, if we have a lot of training examples, what we'll often find is that even though in a plane there are only 3 support vectors, if we have a lot of examples, there will be other points that are kind of close to here, so that if this thing were to move, it might not even remain a support vector anymore. The boundary might be caught by some other one of our many data points, which would suddenly serve as a support vector instead. So this decision surface is not quite as sensitive to the location of this point as we might think, provided there are a lot of other points around that can also suddenly stand up to be support vectors.
But what if the negative one, one of the negative one goes into the group of area of the
Yeah, good. Okay, so you're saying, what if I do have noise in my data and this negative one really happens to be over here? Then I'm toast. So far, we're going to change that. But for what we said so far, we're talking about what I will call hard margin support vector machines, unforgiving. They're assuming that the set of points we're given is linearly separable perfectly. And if they aren't, then the objective function we've set up so far will not be satisfiable. Yes?
What if we want to separate into more than 2 groups? Can we just add more?
Yes. Yeah, so the question is, what if we have not 2 labels, but more than 2 labels, A, B, and C instead of positive and negative? Situation here is actually very similar to what if we wanted to use logistic regression for 3 labels. And you recall there the solution is, instead of learning just one decision function, if we have 3 labels for logistic regression, what we'll do is we'll learn 2, or you could do it either way, 2 or 3 functions. 3 is kind of the most intuitive, 1 per label. And then we just classify a new point according to which of those functions assigns the highest wx plus b. So the situation here for support vectors is similar. There are some details of that we won't go into here, but I'm pretty sure are in the chapter in the book. You have to worry about setting up the optimization function correctly, optimization objective correctly, so that you're simultaneously optimizing the weights of all of the different functions you're learning for the different classes. But the concept is pretty much isomorphic to what we were doing with logistic regression in that case. Okay, so let's go ahead and I want to get to this point of, well, what if there is noise in the data? So keep that in mind. Don't let that go. But so far we're talking about the linearly separable case. But before we go to look at noisy data, let's come back to the idea of kernels. And one thing we can do if we look at our data and see that it's not linearly separable in the base space is, of course, we can project it into some higher dimensional space where it might be linearly separable. And so to do that, one nice way of doing it is to use kernel SVMs, which we can do by just changing our objective a little bit. Our primal version, which used to say, let's multiply wx plus b, now I'm going to introduce some function phi that projects my original data into some higher dimensional feature space. And so now if I want to operate in that, you know, that might be like the quadratic projection that we talked about when we discussed kernel linear regression. Then if I want to work in that space, I'll just apply my projection to any of the points that you give me that are in this initial space. I'll just project them up into that space. I will learn weight vectors W that live up in that projected space and whose squared magnitude is minimum. So it's the same primal objective, it's just I'm mapping everything up there. And now the dual one, though, just like in the linear regression case, the dual problem remains living down in the original space. So again, we have the same objective function we had before for the dual, except now I've replaced the dot product of each training example by the kernel function, right? Equivalently, I could have said phi of xj dot product with phi of xk. Of course, that would be equivalent because this is our definition of a kernel function. For a projection phi, it is the kernel. The kernel function is, by definition, the function for projection phi that has the property that if we give it two vectors, it returns this quantity. But again, it happens, remember that quadratic projection was just taking the original space dot product and squaring it instead of projecting things up into the quadratic space when we talked about linear regression. So here's the same deal. So again, the nice thing is I just replace all my dot products by calls to my kernel function instead. It operates down in the original space. And so I can solve either this problem or equivalently that one, except that this one I can solve down in the base space. And I don't have to project things really ever up into that bigger space. So this is really, you know, somebody asked a question after class the other day that made me realize maybe this key point hadn't gotten through to everybody. When we talk about projecting these points into the higher dimensional space, the nice thing about the kernel approach using the dual form of the objective function is that we never, ever do any computations up in that bigger space. That's only in our mind's eye. Everything that the program does is still in the original low-dimensional space. And that's what makes these kernel methods so valuable in terms of tractability. Okay. All right, so in a nutshell, we can apply the same kernel trick that we applied to linear regression. We can apply that to support vector machines, and it works great. Okay, so what does this look like if you actually do it? So here's a plot of a decision surface learned by a support vector machine, a hard margin support vector machine, where we're showing the points in their original two-dimensional space. Obviously, these points are not linearly separable in the original two-dimensional space. In this case, they're projected into a higher space according to the kernel, which is this Gaussian function. So our kernel function that we're using in this case is just this. And if you recall from the other kernel lecture, this Gaussian kernel actually corresponds to projecting into an infinite dimensional Euclidean space. But of course, we're glad we don't have to actually operate in that. But by just using this kernel function, effectively the algorithm is doing the same thing as if it was finding linear separators in that higher dimensional space, which it's not. But then down here in the original space, this is what the decision surface looks like. And you can see the support vectors. They're the ones that are circled here in green. And you can see the main decision boundary. That's this. That separates these out. And you can see in this case there are what? 1, 2, 3, 4, 5, 6, 9 support vectors that we can see here. So this is pretty cool. This lets us see the kind of highly nonlinear classifiers that we can learn that correspond to linear classifiers up in some, in our heads, imagined projected space. And that in that imagined projected space happen to be the maximum margin linear classifier. And this is what we have down in the ground space. Yeah? Is there an intuition for how to map back and forth between those? Sorry, your question? Yeah. Yeah. So I think of it this way. I think the question is, how do you really pick one of these kernel functions? There are a lot of possibilities, and the intuition is not so clear. I agree. I try to think of it this way. When I pick a kernel function, what I'm trying to choose is a similarity metric. I'm trying to say 2 points that are nearby according to this kernel, whose dot product is large according to this kernel, are very similar. And 2 points whose dot product is small according to this kernel are very dissimilar. And that's how they're going to be used here. So I'm going to take some weighted value of the y label for training example L if my new x, if the kernel for my new x is returns a large dot product with XL. And if it's far from XL, a small dot product, then I'm not going to use that weighted example very much to label x. So I think of the kernel function as basically a similarity metric. Try to pick it so that it assigns high dot product values to 2 points that you. If it assigns high dot product to 2 points, that means you think they're likely to have similar values. And other than that, I don't really have an intuition to give. It makes a little bit more sense if you actually start looking at things like tree kernels and string kernels that people make up, where they say, well, I'll define a kernel function, say over strings, that talks about the number of substrings that they share, for example. And you think, oh yeah, okay, if they share a lot of substrings, then they ought to have labels that are very similar. Okay, so that'll be my kernel function. And so sort of at that informal level, I can accept that, but I don't have a more precise way of thinking about it. Yes?
So how do you optimize for the sigma?
Oh, yeah, the sigma is in here. You can make it up or you can do cross-validation to optimize for it if you dare, which you should.
Yeah, so that means for any data set, you have to do some manual work to determine sigma.
Yeah, I mean, right, there's an infinite family of kernel functions here, depending on which sigma you
What
choose.
if the family has more than one parameter, like a polynomial, it can have dozens of parameters, right?
Right, so you can define kernel functions of all kinds, and if they're parameterized, then in general you have the same problem of picking the value of that parameter. And, you know, our standard way of doing that is some kind of cross-validation.
But what if the parameter space is very high dimensional?
If the parameter space is very high dimensional, you might consider making up a lower dimensional parameter space and using that, or using some seat of the pants heuristic method for choosing the parameters. There's no easy solution. If you decide to do that, you have to make the choice of what sigma is.
Parameters are there in the polynomial kernel?
Oh, this is a very typical, and actually this kernel is very common.
This is the Gaussian, or another name is the radial basis function.
That's right. This is very, this is
So
the,
there's another common kind which is called polynomial. So how many parameters are there?
yeah, there are parameters in all these different kernels, but I don't want to go into the details of listing all the kernels. And this is a prototypical example. We talked about some of the other kernels last time. Okay, yes?
So what are the two positive points used for, on the upper side of the
Oh yeah, what are these things doing over here?
Did the surface go like this, or only, what does the decision surface look like?
Yeah. So these contour lines are contours of equal Wx plus b in the projected space. So that's what we're looking at in these contours. And so what this means is, you know, on this side of the surface here, we're getting positive y values, but they're higher here at the top of this mountain than they are over here as we're going downhill again. And this thing might warp around, and we might see some more negative examples over there. I don't know how this one plays out.
I think it's just because there are no more examples beyond that mountain, so it doesn't matter what happens there.
That's right. So if you think about it, if you think about this is what's going on, that means if we get an x that's like further and further, suppose of all of our training examples lie in this ball, and now I get other x's in the ball, well, I'm going to be multiplying, you know, dot products of my new x with those x. Some of those are going to be pretty big. But as I move further and further and further and further from the ball of training example that I started with, those dot products get smaller and smaller and smaller. And so the values just kind of go back closer to 0. Yeah, I got to be careful. I don't trust my own intuitions thinking about what happens in these high-dimensional spaces. Okay, but I like this picture because it really kind of grounds it out how a linear decision surface in some, in our case, infinite dimensional projected space can be easily dealt with down here in the ground level space and corresponds to a very nonlinear surface, which is characterized by only this handful of support vectors. And those other points really don't even influence what the decision surface is unless they move so far that they become closer to the decision boundary than the current support vectors. Okay, so this is kind of interesting. And so now let's come back to the question you asked about, well, what if the data is not linearly separable? And we just saw one answer. We can project the data into a space where it is linearly separable, perhaps, and then operate there. And that's, you know, that's worth considering. You might get nervous about that if we end up projecting it into a space of, let's say, dimension D, let's say 10,000 dimension, and I only have 500 data points. You might get nervous. But obviously, if I do that, I'm going to be able to find a linear separating plane. So that's one approach. But obviously, that has its drawbacks. And so another approach is to change our objective function. Let's modify it. Instead of demanding that we perfectly label every example, let's allow some mistakes. And so there are ways of doing this. We could, for example, we might think, why don't we just change our objective function, which used to look like this, and we'll just add in another term that says, well, we want to minimize W, but we're going to penalize for making some mistakes. So now we're trying to minimize the sum of the weight magnitude, W, plus some number. We're going to penalize each mistake by some constant C, say. So you can imagine designing different objective functions like that. The problem with this particular one, it takes us out of quadratic programming. So we don't have a simple way to solve that kind of optimization problem. Plus, it's kind of a crude way of dealing with mistakes. It's counting, it's what many people call 0-1 loss function. That is, we're counting every mistake as penalty 1. Actually, C in our case. We're multiplying all the number of mistakes by C. And if you don't make a mistake, you get a penalty of 0. So it's a very all mistakes are equally bad kind of way of thinking of it. So it turns out we can do a better job than this in terms of having smaller penalties for little mistakes and bigger penalties for bigger mistakes. And we can move back into quadratic programming if we do something which is intuitively similar to this, but instead frame this way. So this is what we call soft margin support vector machine. And here you see what we've done is we've said, let's add in this term that's going to capture mistakes with this Greek symbol C. And what C is for any given training example, so this is the sum over training examples. Of how badly, how far we would have to move that example if we wanted to get it on the right side of the decision boundary. Okay, so if I have this red negative example sitting on the wrong side of that decision boundary, I could move it just this distance, C. And if I moved it that far, I can make it, actually it would become a support vector with the right label. So I'm going to, if in fact I'm considering this hyperplane, this W and B, then I'm going to say there's an accompanying C for that training example. And so my objective function is now going to try to minimize the sum of those C's plus my original thing, the magnitude of the weight vector. Because this is how I'm handling with the margin. This will give me the max margin component. And this is mistakes over the training examples. Okay? Now, I also have to change my little constraint here about correctly classifying every training example. Now what I say is, instead of what I used to have, which is, I used to have this, saying that I wanted everything to be on the correct side of the margin. Now I'm saying, well, if that example has a non-zero C, then I'm willing to put up with it. But of course, we're going to pay a penalty for any of those non-zero C's up here.
So are we trying to kind of move the misclassified points until they're correctly classified, or just until they're not misclassified?
We're trying to get them this far, exactly,
Back to being correctly classified.
to be correctly classified. So we're trying to get them all the way to not just to wx plus b equals 0, but to -1, if they're a negative example. Okay. So does this make sense? This is important to kind of get your head around because this is the standard way of handling noisy data with support vector machines. And you see it allows us to trade off these two terms, the number and severity of mistakes over the training examples, plus the size of the margin that we define. And speaking of parameters that we have to choose by hand, this C is just a constant. And we have to choose that C by hand when we formulate the problem. And choosing it tells sort of how much we really don't like mistakes. If I choose a little c, it means I'm willing to put up with more mistakes. If I choose a large c, I say, I really don't want to see too many mistakes. You're going to pay a higher penalty for those. And so maybe you can choose a larger W instead to get rid of those.
How does it help you predict future errors?
How does it help you predict future errors? What we've said so far does not help us predict future errors. But what we'll do, in our classification rule using this is identical to the one we had before. It's still wx plus b, and whether the answer is above 0 or below 0. So so the classification rule, once we've trained, is no different than it was. It's just this is a linear decision surface, and are you on that side or this? But so the difference here is really how do we train? What's the objective we're optimizing when we do train? Okay, so that's our preferred way with support vector machines of dealing with noisy data. Okay, so, and of course, as you might guess, we can not only work in the primal form of that problem. So here are C's added back in. We can also get the dual version of this, which looks almost identical to the dual that we had before, except that our coefficient C ends up here as one of the constraints on the magnitudes of these alphas. So if you flip back through the pages of the slides, you'll notice when we were doing the hard margin classification, we had a constraint here that said the alphas had to be non-negative, but we didn't bound how large they could be. And now when we introduce this soft margin thing, we're bounding how big the alphas can be. But it turns out that's really the only difference. It's kind of surprising. And again, Bishop's book has the derivation of this if you want to go through it. And then happily, these things are still quadratic programming problems. So everything still carries through nicely. And here's an example. So here is, just like the other case, we're looking at points plotted in the original two-dimensional space. But now, instead of using a hard margin support vector machine classifier, here's the soft margin one. You can see the green circles are the support vectors. We have a lot more support vectors now. And you see that our decision boundary is not doing a perfect job. But that's the optimal solution to our objective function. If we, again, use the Gaussian kernel, projecting these original two-dimensional points into a virtual infinite dimensional space where we're learning a linear surface. And, I have to say that decision boundary doesn't look bad given the data. Yes?
I'm still concerned about optimizing for the sigma. So in some cases, so there may be some sigmas. When you use that, it's better linearly separated than when you use other sigmas. So when you do some cross validation to optimize for sigma, can you just compare the optimal object function corresponding to the different sigmas? That is as a measure of both the margin and the errors.
Well, no, the way you would do this, you're asking again about how would we optimize this parameter. And again, the answer is, the way I would do it is I would do cross-validation. I'd take my data, leave out one example. I'd try different sigmas. I'd record how well it worked.
Yeah, so
And I would do that, leave one out way, and then I would choose the sigma value that worked the best.
How to evaluate the performance of a certain sigma? Like,
Right, you look at the leave one out cross-validation error to evaluate which sigma you like
so
best.
only the error or both the error and the margin, or
No, just the error. I mean, if you're trying to optimize how many mistakes you make, then you can look at that. If you want to optimize something else, you can again use cross-validation to optimize that. So let's take this offline. I think that's enough for this direction, because I want to get to some other points before we run out. Okay, so that's it for support vector machines. You know the whole story now. It's actually a very clean, nice story that builds on our kernel idea. So again, our objective, which is very different from the objective functions we've talked about so far. Our objective here is to find the classifier with the maximum margin. We can do this by writing down an objective function. We've seen the primal and the dual forms. The nice thing about the dual is it allows us to do everything in terms of dot products. We can kernelize it, which allows us to do the same kind of finding complicated nonlinear surfaces in our original space that happen to correspond to linear surfaces in some virtual imagined space. We can handle noisy data if we extend it to soft margin with those C slack variables, they're called. And the learning algorithm itself is essentially a quadratic programming optimization algorithm. And there are many of those you can get. There are some algorithms you can download from the web. Things like SVM Lite is a nice package written by Thorsten Joachim, who's at Cornell. Used to be here at CMU as a student for a while. But that's the support vector machine story. And support vector machines are really one of the dominant approaches for practical classification problems these days. And people have extended them in several directions. People work, for example, with support vector regression in addition to classification. And so if you search on support vector in the research literature, you'll see lots and lots of papers extending this idea and kernel methods in general in a lot of directions. Okay, but before we leave this, I want to link it back to some of the other things we've talked about in the course. So what about theory? What can we say about the sample complexity, the number of training examples we'll need to see in order to probably approximately correctly learn something with a support vector machine? So suppose I tell you this. Suppose I have data in a two-dimensional space, like we saw before. I'm using, well, let's say a quadratic kernel function that maps this into 3 points, like the one that we saw before when we did kernel linear regression. So I'm using a kernel that is the square of the dot product in the base space, which corresponds to mapping into a three-dimensional space where I have x1 squared, x2 squared, and x1 times x2 are my 3 dimensions. And now I ask you, how many training examples would I need in order to, with probability 0.9, have a classifier whose error was no worse than 5%, provided I could label all the training examples correctly with my support vector machine? What would you say? I'm getting these expressions like, beats me. No, you're not supposed to say beats me. You're supposed to say, well, let me tell you, because I took the machine learning course. Let me tell you that a support vector machine, even though it's doing these really weird nonlinear things, it actually corresponds to a linear classifier in a high dimensional space. And do you know what the VC dimension is of a linear classifier in a space of dimension D? D plus 1, right. So when I project those 2 points up into this 3-dimensional space, I'm working with a linear separator that has VC dimension 4. And I can apply my old favorite, here's the number of examples I'll need if I want to bound the error to at most epsilon with probability at most 1 minus, or with probability at most delta of violating it. Okay? And this is the slide that I just copied that we used before in our previous lecture on VC dimension, where we pointed out that linear separating planes in n dimensions are just have VC dimension n plus 1. So this is cool. You already know a key result that lets you characterize the complexity of a sample complexity, number of examples we'll need, given some epsilon and delta bounds. You can bound it in terms of the dimensionality of that virtual space in which that virtual linear separating plane is working. And the agnostic bounds would handle the case where you don't have perfect classification error as well. So that's pretty cool. So this just hooks right into what we talked about before. Now, when we started talking, when you brought up the question about noise and having points that aren't linearly separable, we quickly mentioned that, well, we could, if we blow this up into a high enough dimensional space, like where we have more dimensions than we even have data points, then clearly we'll get a linear separator. But everybody kind of recoiled in horror at that idea, correctly. But it brings up the question of, well, how would we choose how high a dimension we're willing to go up to? So we have this design choice. We can blow our points up into some higher dimensional space where we know we're going to have a better chance of linear separation. Our other design choice is we can use soft margins and allow and set that coefficient C to determine how heavily we're going to penalize making mistakes. So we have these two choices. We can blow up into a very high dimensional space and guarantee we'll get 0 errors, or work in some slightly lower dimensional. How do we play that trade-off? And Vapnik, do you remember that name? He's the V in VC dimension. He's also one of the key inventors of support vector machines. That's not why there's a V in support vector machine. But his suggestion was this. So, and this again is a slide from what we saw before. So if you rearrange our expression about sample complexity and the relationship between the training error and the true error in terms of VC dimension, we get this expression. And so Vapnik said this. He said, well, you know, I could work in hypothesis space H1. Maybe that's linear separator planes in 1 dimension, or in 2 dimensions, or in 3 dimensions, or in 4 dimensions. And of course, I'll have more and more hypotheses I can express as I increase them. I'll have a higher VC dimension. And so what he said was, why don't we minimize, why don't we pick the VC dimension and equivalently the hypothesis space, the dimension we're going to project up into, in order to minimize this? As we know, our training error is going to be smaller than our true error. Our true error is going to be bigger than the training error because we're fitting the hypothesis to the training error. But by how much? Well, that's what VC dimension pack theory tells us, by how much. And so he was saying, why don't we pick it to minimize this quantity to the right of the inequality? Because that's actually a bound on the true error that I'm going to experience in the future on future test data for hypothesis H. So what I had to maximize is not necessarily I don't want to necessarily minimize the training error. I want to minimize the training error plus this quantity, which depends on the VC dimension, which depends on how big a space I project up into. And because this is a bound on the true error, it's the true error in the future that we actually want to optimize. So I like this idea. It's very elegant. Unfortunately, it's too loose a bound to be really very useful in practice. But it's a nice idea. And it also is a nice link back into VC dimensions. Yes? Yes. Very good point. So the problem with the Gaussian kernel is it projects us into an infinite dimensional space, hence has a VC dimension of infinity plus 1. So that's an unfortunate thing because it makes this bound rather vacuous. So it's kind of too bad about that. But that does raise a question about is there some other way that we can use somehow the margin to get a sample complexity result instead of the VC dimension? And the answer is yes. So there's a lot of interest in these days in can we use the observed margin, the size of that margin, to say something about future error. And here's the result. Let's just go through it together. So let's start with this part, which should be very familiar. It's exactly what we talked about when we defined our PAC learning setting previously. So we consider some fixed distribution D over training examples XY pairs, where X lives in some D-dimensional Euclidean space. And furthermore, in this case, we're going to assume that all of those vectors have magnitude 1. And just like support vector machines, we're going to assume that Y is not 0 and 1, but minus 1 and 1. And we're interested in finding a weight vector whose magnitude is 1 such that the sign of this, so Wx predicts Y. We're just leaving out the B. It's Wx with a B equals 0 predicts Y. And gamma, again, we can think of gamma as our margin. Then for any positive gamma, the error rate, W, on this underlying distribution, so D is also our P of X, relative to margin lambda, will be this. So this is the true error. For weight vector W and distribution B is just defined as we've defined it before. It's the probability that a randomly drawn XY pair from that distribution will be so bad that it falls inside, here's the positive side, here's the negative side. If W times X times Y is less than lambda, that means we're lying inside this margin. Okay. So we might still be classifying it correctly, but it's too close for comfort. We want the safety margin of gamma. So if we define this, it's really a definition. We define this to be the true error with safety margin gamma. Then here's the result. Let S be a sample of M training examples, drawn IID from the underlying P of X. The sample S can be viewed as an empirical distribution on pairs, fine. We're interested in bounding L0. That's the true error, even if we don't require the safety margin, if our safety margin is 0. So in other words, we're trying to relate the the true error that we might see on the oh, well, let's get to the statement. We're interested in bounding the zero margin error. Actually, you know, the error we'll get if we actually classify things based on whether Wx is positive or negative. And we're interested in bounding that in terms of the margin, safety margin error that we observed on our training sample. Then here's the result. So this is, D again is P of X. So this is the true error using Wx is greater than or less than 0 without a margin, without requiring a margin. And he says this is bounded as the error that we see in the training sample with this safety margin gamma. So that's our observed margin on the training set error, plus this quantity, where again, M is the number of examples. And delta is the same delta as in the PAC learning stuff. So delta, 1 minus delta is the probability of successful learning. Delta is the probability that the version space won't be epsilon exhausted. Okay, so this is interesting. So what's interesting about this, a couple things. One, we're using the margin to tell us basically how the true error will depend on the training error plus this quantity. See, that's just like the thing we looked at here. We're looking, the true error depends on the training error plus some quantity, but we had to use VC dimension. Now we're using instead the margin. So the margin squared is playing a similar role to what the VC dimension was playing before. Not exactly the same expression, but this is essentially the true error. If we end up with margin gamma on the training set with 0 errors, or in the soft margin case with some errors, let's assume the hard margin case where we train and get 0 training error, then our true error is bounded by the rest of this stuff. And in either case, the deviation between the training error and true error is bounded this way. So the margin is playing a very interesting role that's kind of like the role of the VC dimension. And it will play it even in the case that we use the Gaussian kernel. That's what's cool. Because the dimension of the space we're projecting into is not mentioned in this result, even though it's implicitly mentioned here when we talk about the VC dimension. That depends on how big is the space we're exploding into. But this expression that only mentions the margin and doesn't, and that's the margin, so it's not, doesn't actually mention what D is. Yes? How do you calculate the margin? I believe it should be easy, right? The margin is just the dot product calculation. So we can calculate it down in the ground space with kernels. That's a good exercise. That would be an excellent homework question. Yes?
These formulas tend to have strange mathematical constants in them, like 84 and...
Yeah, I hate that. 27.18 is...
Are these coming from somewhere? Are they rounding or something?
Many of them are rounding things, and they're just trying to get it into closer to printable on one line form. Yeah, so tighter bound, actually there's a tighter bound than this, which is less readable, which is available. Okay. So the bottom line is there's interesting map back to our old friend PAC learning theory. And the final thing, just one slide I want to talk about, is in practice, by the way, when I use support vector machines, I get answers I get accuracies that I find are very similar to when I use regularized logistic regression. And I had wondered about that for a while, and then I ran across this nice result where, which is also in our textbook, it's in the chapter of the required reading, looking at what is the objective function for support vector machines and how does that actually relate to the objective we're maximizing for logistic regression. So let me just leave it at this. So if I plot the penalty that we're paying as we make a mistake as a function, so this axis is the penalty, and here's my penalty, as a function of this quantity, wx plus b times y, the prediction, the value output by the support vector machine. Essentially what this is saying is, if my margin is 1, then as long as this value is greater than 1, I'm on the right side of my margin boundary. I don't have to worry. But if I get too close to 0, I start paying a penalty. C becomes non-zero. And in this case, the penalty is just C times C for xj. And that gives me this funny function of this, which we call the hinge loss. It's saying, you know, how badly you do on x, predicting it, is you pay a penalty that looks like this hinge function. We could compare that to a 0-1 loss, where we say we pay no penalty unless we're on the wrong side of the margin, or the wrong side of the decision plane, then we pay a penalty of 1. And you can see what support vectors machines are doing is this hinge loss, which they use, is very different. But if you remanipulate the logistic regression loss function and plot it in a similar scale, you get this blue one for logistic regression loss function. And you can see what it's doing is actually very similar to tracking this hinge loss. And the main difference is that is this discontinuity in the hinge loss, which means in terms of solving the optimization problem and applying the final dual form, we can ignore anything that has that's operating over here because it's not close to causing a penalty. Whereas the logistic regression function, you know, you pay a penalty even if you label a positive example as positive with probability 0.99, you still pay a penalty of 0.01. So the penalty you pay in logistic regression continues even as you're doing the correct classification, so long as some of the probability mass is misassigned. So I find this an interesting, intriguing way of thinking about the relationship between some of these methods. I just wanted to expose you to that. Okay, thanks. We're running a little late, so I'm going to let you go. And no class Thursday. It's Spring Carnival.